Dear students, let us discuss about the first unit of EDC. Unit name is diode. The topics include diode, static and dynamic resistances, equivalent circuit, diffusion and transition capacitances, VI characteristics, diode as a switch and switching time. So these are the topics in unit 1. Let us discuss about each and every topic in a great detail. So first let us study about the basics of this unit. A PN junction diode is different from a PN junction. A PN junction is the boundary or interface between two types of semiconductor materials. Here you can see in the figure a P-type semiconductor material and an N-type semiconductor material are fused in order to form a PN junction. So in a P-type we will be doping it with trivalent impurities such as boron, aluminium, gallium, indium or titanium. In an N-type semiconductor, we will be doping it with pentavalent impurities such as phosphorus, nitrogen, arsenic, antimony or bismuth. So, the main reason for doping is in order to increase the number of charge carriers on p-type and on n-type. So p-type means positive and n means negative. In p-type we will be having excess of holes and in n-type we will be having excess number of electrons. We will be fusing both p-type and n-type semiconductor materials, and one more important point is we need to use same type of material on p-type and on n-type. If we are using silicon here, we need to use silicon here also on n-type. If we are using germanium, we need to use germanium on n-type also. If we are using different type of material, that would introduce a defect called as grain boundary, which will decrease or reduce the thermal conductivity and it will reduce the overall performance of the diode. So if we connect two electrodes, one at P side and another at N side, so two electrodes, that would form a PN junction diode. So this is the image of a PN junction diode. This is P-type region, this is N-type region. P-type region is connected to anode A and N-type region is connected to cathode K. P side it is positive and N side it is negative. And this is the symbol of a PN junction diode. PN junction diode allows the current flow only in one direction and it blocks the current flow in other direction. So this is the PN junction diode. You can see here this silver side is negative. If we see the discrete components in our laboratory, this side indicates positive and the silver side indicates the negative terminal. So in order to study the working of a PN junction diode, we need to study its biasing conditions. So we will have three different types of biasing conditions. The first one is no bias condition, the second one is no bias or zero bias, the second one is forward bias condition, and third one is reverse bias condition. Here in this figure you can see that it is no biased condition. Biasing means addition of or application of external voltage to the diode. So here the two terminals anode and cathode are not connected to any battery source, so we can say that it is in no bias condition. In no bias condition, we will be having in a p-type we will be having excess number of holes than n side, and in n side we will have excess number of electrons when compared to p side. So there is potential gradient of charge carriers on both p side and n side. So majority charge carriers and at p side are holes, they will move towards the junction and they will move towards the n type, and majority charge carriers at n side are electrons, they will move towards the junction because of potential gradient. So what it will be happening? So due to the potential gradient, majority charge carriers at p side and n side will diffuse from one region to another region. The diffusion, the movement of majority charge carriers is called as diffusion, and the current is produced because of the movement of majority charge carriers. That particular current is called as diffusion current. So majority charge carriers will be coming near the junction and they will be recombining at the junction, and they will form a depletion region at the junction. Depletion region is depleted of free electrons, so there will be no any free electrons in the depletion region, and depletion region will not allow the further movement of electrons and holes, so no current is produced hereafter. So here you can see that depletion region is formed in a PN junction diode. Even we did not apply any external voltage to the diode. Depletion region is formed. You can observe in the second figure here. This is the depletion region. So width of the depletion region is WD. It is denoted with WD. You can observe clearly in this figure. Depletion region is formed. So negative ions, positive ions. We will have acceptor ions at P type and we will have donor ions at N side. So this is the width of the depletion region or depletion width during unbiased condition. This complete thing we will denote it with W suffix D. So the next biasing condition is forward bias condition. In a forward bias condition, we will be connecting P type semiconductor to the positive terminal of the battery and N type to the negative terminal of the battery. So in P type semiconductor we will be having excess of holes, and in N type semiconductor we will be having excess number of electrons. So due to the positive terminal of the battery, holes will be repelled towards the junction and electrons in N side will be repelled towards the junction. And if we increase this voltage, diode voltage further, diode voltage is denoted as VD. If we increase this further, electrons and holes will cross the junction, will cross the depletion region, and they will try to move towards the junction. So in this way the width of the depletion region will be reduced in the forward bias condition. The third type of biasing is reverse biasing. So to the P type we will be connecting negative terminal of the battery, and to the N type we will connect positive terminal of the battery. So in P type we will be having excess number of holes. They will be attracted towards the negative terminal of the battery, and in N type we will be having electrons. They will be attracted towards positive terminal of the battery, and this will increase the width of the depletion region. So in reverse bias condition, width of the depletion region will increase, and in forward bias condition, width of the depletion region will decrease. If we compare the widths of depletion regions in all the three cases, width of the depletion region in reverse bias is more than width of the depletion region in no bias or zero bias than the width of the depletion region in forward bias condition. So if we observe the VI characteristics of a PN junction diode, on x-axis we will be having the voltage VD, and on y-axis we will be having the current ID. So during forward bias condition, as we increase the voltage, the current will increase, and if it reaches the barrier potential, that is 0.7 for silicon and 0.3 for germanium, the current will increase rapidly. So we can see it from this graph. In forward bias condition this is the case, and if we see the reverse bias condition, as we increase the voltage the current increases, and if it touches the breakdown voltage or knee voltage, the current will increase rapidly. So at this stage the breakdown will happen, breakdown of the diode. And in reverse bias, as the majority charge carriers, electrons and holes will be attracted towards the terminals of the battery, the current flows only because of the minority charge carriers. That current will be very small, that will be in microamperes. So let us go through the material ones. About PN junction, it is the boundary or interface between two types of semiconductor materials, that is P type and N type, inside a single crystal of semiconductor. P means positive side, it contains excess of holes, and N negative side, it contains excess of electrons. This allows electric current to pass through the junction only in one direction. The PN junction is created by doping. Doping means addition of impurities. If two separate pieces of materials were used, this would introduce a grain boundary between the semiconductors that would severely inhibit its utility by scattering the electrons and holes. The PN junctions are elementary building blocks of semiconductor electronic devices. So PN junctions are the basic building blocks in order to manufacture the diodes, transistors, solar cells, LEDs and integrated circuits. So in order to manufacture a BJT, we will be connecting two PN junction diodes back to back. Next one is PN junction diode. So we are connecting two electrodes, anode and cathode, to the PN junction. So in a p-type semiconductor we will be having holes as excess charge carriers and acceptor ions. In an n-type we will be having electrons are the majority charge carriers and we will be having donor ions, and this is the junction. It is the boundary or interface between p-type and n-type semiconductor material. So PN junction diode is a two-terminal device, and there is a difference between PN junction and PN junction diode. We obtain PN junction diode by attaching two metal contacts to PN junction. We already know this. Because of this, we have three different possibilities. So to study the working, no bias condition or zero bias condition, forward bias condition and reverse bias condition. What is biasing? It is the application of external voltage across two terminals. So in case of p-type semiconductor, we add trivalent impurities. Due to this, we have holes as the majority charge carriers and electrons are the minority charge carriers. In the case of n-type semiconductor, we add pentavalent impurities. Due to this, we have electrons as the majority charge carriers and holes as minority charge carriers. And minority charge carriers depend only on the temperature, because electrons gain thermal energy and they break the covalent bond. It does not depend upon the external voltage that we are applying. At p-type we have acceptor ions and holes are the majority charge carriers. At n-type we have donor ions and electrons as the majority charge carriers. The concentration of holes is higher at p side than n side. Because of this, we have concentration gradient of holes from p side to n side. Similarly, we have concentration gradient of electrons from n side to p side. Due to this, we have holes, or due to this, holes move towards n side and electrons move towards p side. So due to this movement of majority charge carriers across the cross sectional area, there will be current. This process of movement of charge carriers from high concentration to low concentration is called diffusion, and the current that is produced is called as diffusion current. So the diffusion current is due to the movement of majority charge carriers from higher concentration to lower concentration. Because of diffusion, holes on the p side combines with electrons on n side, and electrons on n side combines with holes on the p side. So the immobile ions which were fixed and covered initially will get surface out because of diffusion. Initially, electrical neutrality was maintained. With the acceptor ions we had holes, and with the donor ions we had electrons. As holes are combined with electrons, we are left with immobile ions. So because of this, depletion region or depletion layer is formed at the PN junction. The other name of depletion region is space charge region. Depletion region has only immobile ions, as holes and electrons gets combined. So this is the depletion region, you can see here. So this depletion region acts as a potential difference. Because of this potential difference, there is electric field that is denoted with E. It will be from right to left, that is positive to negative. The width of the depletion region is fixed. Because of this, there is no movement of charge carriers, as the positive layer repels the holes and negative layers repels the electrons from n side. So the potential is acting as barrier for the further movement of free charge carriers. Hence we call it as barrier potential or built-in potential. In the case of p-type, electrons are the minority charge carriers, and at n-type, holes are the minority charge carriers. So because of the electric field intensity E, electrons move to the right and holes move to the left. So due to the movement of or drift of minority charge carriers, current is produced. This current is called as drift current. The direction of drift current is opposite to that of diffusion current. Under a steady state condition, diffusion current and drift current are equal. So the net current is equal to 0 for open circuited PN junction diode. Next one is the forward biased condition. So you can see that positive terminal is connected to positive P side and negative terminal is connected to N side. So here, due to the repulsion force, width of the depletion region will decrease. So initially the voltage VD is applied to this PN junction diode, and if we keep on increasing the voltage, the width of the depletion region decreases, and the current ID is given by the current due to majority charge carriers minus the current due to minority charge carriers. Minority charge carriers current, it remains same even if we increase or decrease VD, because it will depend only on the temperature and it will not depend on the voltage that we are applying. So initially the width of the depletion region is WD and initially the barrier potential is VB. If we increase the voltage VD, width of the depletion region decreases and barrier potential also decreases. So new barrier potential can be given as VB minus VD. VB is 0.7 volts for silicon and it is 0.3 for 3 volts for germanium. The next case is reverse bias condition of a PN junction diode. So we will be connecting it in reverse bias. P type semiconductor is connected to negative terminal of the battery, N type is connected to positive terminal of the battery. Because of attraction force, all the holes from P side will be moved towards negative terminal of the battery and electrons will be moved towards the positive terminal of the battery, and only minority charge carriers will be there at P side and N side. So the current that is produced in this PN junction diode is due to minority charge carriers only. So we denote the current with IS, that is in the units of microamperes. So barrier potential in reverse bias condition can be given as barrier potential, initial barrier potential plus the voltage that we are applying across the diode. If we increase this VD, diode voltage, the barrier potential increases and width of the depletion region also increases. If we compare the width of depletion regions of three cases, no bias condition, zero bias condition and forward bias condition, width of the depletion region in reverse bias condition is greater than width of the depletion region in no bias condition than the width of depletion region in forward bias condition. If we compare the barrier potential in all the three cases, barrier potential in reverse bias condition is greater than the barrier potential in no bias condition than the barrier potential in forward bias condition. So these are the VI characteristics of a PN junction diode. For till 0.3 volts, as the voltage increases, current will increase very slowly, and if it touches 0.3 for germanium semiconductor, current will increase rapidly or exponentially, and if it touches 0.7, that is for silicon, the current will increase in this way. And in reverse bias condition, the current is due to minority charge carriers. For germanium, if it touches the knee voltage or breakdown voltage, then the current will increase rapidly, and for silicon it will increase in this way in reverse bias condition. There is a term called peak inverse voltage. It can be given as PIV or PRV. It means that the maximum voltage that a diode can withstand in the reverse bias condition before breakdown. So it is also called as reverse breakdown voltage. So now let us see the effect of temperature on VI characteristics. If we increase or decrease the temperature, how the VI characteristic curve changes. So on increasing or decreasing the temperature, VI characteristics of PN junction diode changes significantly in both forward and reverse bias. So the effect of temperature is different in both forward and reverse bias regions. Let us consider the VI characteristics of a silicon diode to understand the effects of temperature. So the barrier potential of silicon diode is, we know that it is 0.7 volts. Once the applied voltage across the diode is equal to 0.7, there is an exponential increase in the current. So let us see in the forward bias condition. The characteristics of silicon diode shift at the rate of 2.5 millivolts per degree centigrade rise in the temperature. So if we increase the temperature, the characteristics of silicon diode shift to the left at a rate of 2.5 millivolts, so that the plot will shift to the left. On decreasing the temperature, the plot shifts towards the right. So if we increase, so initially the temperature is 25 degrees centigrade. If we increase temperature, that is if we increase 100 degrees, the total temperature will be 125. So the plot will move towards left. Here we can see clearly the plot has moved towards left. And if we decrease the temperature, 25 minus to 100 degrees, 100 degrees if we have decreased, it is minus 75, the plot will shift towards right. And in reverse bias, in the case of reverse bias region, the reverse saturation current IS doubles for every 10 degrees centigrade rise in the temperature. So for 100 degree rise in the temperature, or at 125 degrees, so at 25 degrees let us consider it as 10 nanoamps. At 35, it means that 10 degrees centigrade has been raised. So it is doubled, 10 is doubled to 20. Next, for 45 degrees, we have to double it, 40 nanoamperes. For 55, we have to double this 40, 80. And at 125, we will be getting 10,240 nanoamps, that is 10.24 microamperes. If we see the graph, so initially graph was at 25 degrees. If we have increased 100 degrees, so it will become 125. For 125, the current is 10,240, and for minus 75, the current is 10 nanoamps. So if we have decreased this, the current is very less, 10 nanoamps. This is all about effect of temperature on VI characteristic. The next topic is diode resistance. So we have three different types of diode resistances: DC or static resistance, AC or dynamic resistance, and average AC resistance. The diode will offer some resistance to flow of current. So we have these three types of cases. So let us see about each and everything. DC or static resistance, it is the ratio of DC voltage across the diode to the direct current flowing through it. So we know that V is equal to IR, and R can be given as V by I. Here we have DC resistance, so RDC equal to VDC by IDC, or RD is equal to VD by ID. So in the forward bias condition, we can draw the graph like this, and if we mark some points OA and OB, we can give like V by I can be given as, V is on x-axis and I is on y-axis. V by I can be given as OA by OB. So the resistance at point P can be given as OA by OB. Second one is AC or dynamic resistance. So if we apply an input AC signal or alternating input to the circuit, it is defined as dynamic resistance. So the operating point Q is not fixed here in case of AC. It will move to Q1 and then it will move to Q2 depending upon the input. So in the case of AC resistance, as the input varies, the voltage and the current will not remain same. VD is the voltage across the diode. Initially its value is 0. Because of this, the current through the diode ID is also equal to 0. So if V is 0, then I is also 0. When VD changes, the current through the diode also changes, and the operating point Q changes significantly. Operating point moves to Q1 when we have maximum voltage and current. The operating point moves to Q again when the voltage and current are 0. and Q moves to Q2 if the current decreases and the voltage across the diode decreases. So the operating point across the diode, operating point moves up and down. So here you can see that this is the input voltage that we are applying. So this is the voltage. Initially it is at Q. If operating point, if this increases, if voltage increases, then it moves to operating point moves to Q2, then again it comes back to Q, then again it goes to Q1, then again it comes back to Q. So operating point will not remain same, it will move up and down. So this can be given as AC or dynamic resistance can be given as small rd or RAC. This is also change in voltage by change in current, delta Vd by delta Id, and the value of Rd is equal to 26 millivolts by Id for numerical calculations. The next one is diode current equation. It is given as Id is equal to Is into e power Vd by eta Vt minus 1, where Id is diode current, Is is reverse saturation current at room temperature, Vd is external voltage applied to the diode, eta is ideality factor, its value is 1 for germanium and 2 for silicon, Vt is nothing but Kt by Q, which is equal to T by 11,600 thermal voltage. K, here K is Boltzmann constant and its value is 1.38 into 10 to the power of minus 23 joule per Kelvin. Q is nothing but the charge of electron, its value is 1.6 into 10 to the power of minus 19 coulombs. T is temperature of the junction in Kelvin. At room temperature, Vt is equal to 26 millivolts. And the last one is average AC resistance. The average AC resistance is the resistance determined by the straight line that is drawn between the two intersections obtained by maximum and minimum values of input voltage. So this is the minimum value of input voltage and this is the maximum value of input voltage. If we join these 2 points, minimum voltage and maximum voltage, with a line, that line will determine the average AC resistance. So it is given by RAV. RAV is equal to delta Vd by delta Id. So the next topic is diffusion capacitance. When a PN junction is forward biased, the potential barrier or the width of the depletion region will decrease. As a result, electrons from N region enter into P region and holes from P region enter into N region. So upon diffusion, the density of charge carriers near the junction is very high. So it acts as a diffusion capacitance. What is capacitance? It is the ability to store the charge. So at one side, all the positive charges will be accumulated and at other side all the negative charges will be accumulated. So a capacitor will have positive charges at one plate and negative charges at one plate, and in between it is separated by a dielectric medium. So here also the PN junction diode is acting as a capacitance. All positive charges or holes will be accumulated at one side and electrons will be accumulated at other side, and the depletion region is acting as an dielectric medium. So the ratio of change in stored charge outside the depletion region to the change in applied voltage is called as diffusion capacitance. It is denoted by CD. CD is diffusion capacitance. So we can write it in this way. Change in stored charge. Change in charge is given by dq. To the change in applied voltage is given by dV. So CD is equal to dq by dV. So we know that diode current equation Id is equal to Is into e power Vd by eta Vt minus 1. Id is the diode current and we have a new term here, tau. Tau is the mean lifetime of charge carriers, that is electrons and holes that are diffused. So we can say that the current is flow of electrons per unit time. So Id can be given as Q by tau. So Q can be written as, if we cross multiply Id and tau, we will get Q. Q is equal to Id into tau. So if we substitute the Id from diode current equation in the place of this, we will get Q is equal to Is into e power Vd by eta Vt into tau. We have substituted the value of Id here. and we have to differentiate this equation number 4 with respect to VD, because we need to obtain the capacitance, diffusion capacitance, that is our aim. So if we differentiate this equation number 4 with respect to VD, we will get dq by dVd is equal to d by dVd of Is into e power Vd by eta Vt into tau. So Is and tau are constants. So if we differentiate this e power ax term, we will get e power ax into a. So a is 1 by eta Vt here. This is like e power ax, differentiation of e power ax with respect to x. Here x is Vd. So e power ax into 1 by into x. So we will get e power Vd by eta Vt into 1 by eta Vt. So we can write dq by dVd is equal to Is into tau by eta Vt into e power Vd by eta Vt. So just rearranging these terms, Is e power Vd by eta Vt into tau by eta Vt. From the diode current equation we can get, if we expand this, Id is equal to Is into e power Vd by eta Vt minus Is. So Is into e power Vd by eta Vt can be written as Id plus Is. So that is what we have written here. Is into e power Vd by eta Vt can be written as Id plus Is, that is from diode current equation, into tau by eta Vt. Id is the diode current and Is is the current due to minority charge carriers. If we compare both these currents, Is is very small when compared to Id, so we can neglect it. So dq by dVd is equal to Id into tau by eta Vt. So Cd is equal to dq by dVd is equal to Id into tau by eta Vt. So we can see that the diffusion capacitance is directly proportional to forward bias current. From this, it is directly proportional to Id. So it is forward bias current. So the next topic is transition capacitance. We know that the capacitor store charge in the form of electric field. This charge storage is done by using two electrically conducting plates placed close to each other, separated by an insulating material called as dielectric medium. The conducting plates or electrodes of the capacitor are good conductors of electricity, therefore they easily allow electric current through them. On the other hand, the dielectric material or medium is poor conductor of electricity, therefore it does not allow electric current through it. However, it efficiently allows the electric current. So we can see the charged conductive plates here. So this is the dielectric medium. These are the positively charged, these are negatively charged, and these are connecting wires. These orange color are represented with electrons, and these are holes. So when the voltage is applied to the capacitor, the charge carriers start flowing through the conducting wire. When these charge carriers reach the electrodes of the capacitor, they experience a strong opposition from the dielectric. So the next topic is transition capacitance of a PN junction diode. It is denoted with CT. So let us see how it acts as how a PN junction diode in reverse bias acts as transition capacitor. So this is the reverse bias condition. So in the depletion region, the electric charges, that are positive and negative charges, do not move from one place to another place. They will be fixed at their places. However, they exert electric field or electric force. Therefore, the charge is stored at the depletion region in the form of electric field. So this is the depletion region. Here the charge is stored in the form of electric field. The ability of a material to store the electric charge is called as capacitance. Thus, there exists a capacitance at the depletion region. And the capacitance at the depletion region changes with the change in the applied voltage Vd. When reverse bias voltage is applied to the PN junction diode is increased, a large number of holes, that are majority charges from P side and electrons, majority charges from N side, are moved away from the junction. As a result, the width of the depletion region increases, whereas the size of P and N region decreases. P and N regions are acting as plates. We know that the capacitance means the ability to store electric charge. The PN junction diode with narrow depletion width and largely p-type and n-type region will store large amount of electric charge, whereas the PN junction diode with wide depletion region and small p and n-type regions will store only a small amount of electric charge. Therefore, the capacitance of the reverse bias in PN junction diode decreases when the voltage increases. The change of capacitance at the depletion region can be defined as change in electric charge per change in voltage, same as diode diffusion capacitance. There CD is equal to dq by dVd. Here Ct is equal to dq by dVd. Ct is transition capacitance, dq is change in electric charge, and dVd is the diode voltage. The transition capacitance can be mathematically given as Ct is equal to epsilon A by W, where epsilon is the permittivity of semiconductor, A is area of plates or p-type and n-type regions, and Wd is the width of the depletion region. And the next topic is diode switching times. The major application of a diode is it will act as a switch. So we use switches mainly to turn on or off. Switches are basically of two types: mechanical switches and electronic switches. Mechanical switches we need to apply pressure to turn on or off, and for electronic switches no need of applying any pressure. They are very convenient to use. They are used for simple or less power consuming applications. Like diodes and transistors are the types of electronic switches. So now the diode switching times, this is the last topic. The time taken by the PN junction diode to turn on from off state or turn off from on state is called as switching time of the diode. The time taken before the diode recovers to its steady state is called as recovery time. Steady state is nothing but on state or off state. So we have two different types of recovery times. The first one is forward recovery time. It is denoted as TFR, that is from reverse bias to forward bias. And second one is reverse recovery time, that is TRR, forward bias to reverse bias. So forward recovery time TFR is the time interval taken by the diode to switch from reverse biased state to forward biased state is called as forward recovery time TFR. You compare these recovery times, switching times with a fan, so that you will understand it more clearly. Reverse recovery time TRR can be given as the time interval taken by the diode to switch from forward biased state to reverse biased state is called as reverse recovery time, which is denoted as TRR. Generally, reverse recovery time is greater than forward recovery time. So we have some notations here. The majority charge carriers in p-type are holes that are represented with p0. The majority charge carriers in n-type are electrons that are denoted by n0. Minority charge carriers in p-type are electrons that are denoted by np0. This suffix p0 will represent the type. So for p-type we will have p0 here, and for n-type we will have n0 here, and this n will represent the minority charge carriers or majority charge carriers. So in minority charge carriers in p-type are electrons, so we will represent it with np0. Minority charge carriers in n-type are, first we need to write suffix because we are talking about n-type here, so n0. Minority charge carriers in n-type are holes, so we will write it with p and n0. So if we see the energy band diagrams in all the three biasing conditions, for no bias or zero bias condition we are not applying any external voltage, so we will represent the diode like this. Here PN junction diode is open circuited, so we will be drawing the energy band diagram. So this is the junction, and this is p-type, and this is n-type. At p-type the majority charge carriers are holes, we will represent it with p0. At n-type majority charge carriers are electrons, we will represent it with n0, and we will represent the majority charge carriers always with a thick line and minority charge carriers always with a dotted line. Minority charge carriers at p-type are electrons, we will represent it with NP naught, and minority charge carriers at N type or holes, we will represent it with NP naught. So in open circuited PN junction or no bias or zero bias condition of a PN junction, there will be no movement, there will be no any current flow. So we will represent it in this way only. And coming to forward bias condition, P-type semiconductor is connected to positive terminal of the battery, N-type semiconductor is connected to negative terminal of the battery. So the energy band diagram will be like this. First we need to represent P-type, N-type, and we need to denote all the majority and minority charge carriers. So the majority charge carriers in P-type are holes. Upon increasing the voltage, holes will diffuse to N-side, and in N-side the holes are the minority charge carriers, so they will become minority charge carriers after entering into N-type region. So these are the excess minority charge carriers. So Pn minus Pn naught will give us the excess minority charge carriers. Pn is the total number of holes and Pn naught is the number of holes that are present in N region. Pn minus Pn naught will give us the excess minority charge carriers. Similarly, Np minus Np naught will give us the total number of minority charge carriers on P side. So majority charge carriers in N side will be moved towards P type, and there they will become minority charge carriers. So on P side there are excess minority charge carriers. So we can get it by Np minus Np naught. The minority charge carriers move away from the junction while majority charge carriers move towards the junction. On increasing the voltage, the holes on P side diffuse towards N side and electrons on N side will diffuse towards P side and obtain or reach the steady state. So there will be excess minority charge carriers on both P side and N side. So upon increasing the voltage, here holes will diffuse towards N side and electrons will diffuse towards P side. So on both sides there will be excess number of minority charge carriers. The current will flow through the junction. And in reverse bias condition, we will connect the P-type semiconductor to negative terminal of the battery and N-type to positive terminal of the battery. Majority charge carriers does not conduct the current at the junction in reverse bias. So current due to majority charge carriers in reverse bias is 0. So from forward bias region, we make a diode to be in reverse bias. So if the fan is on initially, we will try to make it off. So large amount of current flows for a very short time. If you are trying to turn off a fan, large amount of current will flow before the fan gets completely off. The current flows till all the excess minority charge carriers at P side and N side are removed. So how to represent the graph? This is P side, this is N type. We need to represent the majority and minority charge carriers using their notations, and this is the graph or energy band diagram. So this is the input voltage. The first graph shows that input voltage from 0 to T1, the diode is on. At T1 we are trying to turn it off. So if we are trying to turn it off, excess minority charge carriers will be present and the diode will be in off condition till all the excess minority charge carriers are removed. Ideally it should be in this way. The diode current, this is the graph representing the diode current. Ideally it should be like this, ideal response, but practically this is the case. So from T1 to T2 it is denoted as Ts, and from T2 to T3 the time is denoted as Tt. Ts is the storage time and Tt is the transition time. The total transition time and storage time is given by TRR. TRR is nothing but the reverse recovery time. TRR is equal to Ts plus Tt. And the last one is the diode voltage. So at T1, this is about the third graph explanation. At T1, the diode suddenly brought to off state from on state. It is known as storage time. The diode is at this point T1, the diode is suddenly brought to off state from on state. So we call it as storage time. Storage time is required to remove all the minority charge carriers, excess minority charge carriers. Next, the next time period is transition time from T2 to T3. T2 to T3 is the transition time. It is the time taken by the diode to get completely into open circuited condition. After T3, the diode will be in steady state reverse bias condition. It means it will be completely off. The applications of diode switching circuits, high speed rectifying circuits, they are used in high speed rectifying circuit, they are used in high speed switching circuits, they are used in RF receivers, they are used in consumer applications, they are used in telecom applications, etc. The applications of the diode is PN junction diodes are they are used in clippers, clampers, signal mixers, signal demodulators. There are various applications. Go through all the applications of PN junction diode. The last topic is diode equivalent circuit. An equivalent circuit is the combination of elements properly chosen to best represent the actual terminal characteristics of a device, system, or such in a particular operating region. In other words, we can say that once the equivalent circuit is defined, the device symbol can be removed from a schematic and the equivalent circuit can be inserted in its place without severely affecting the actual behavior of the system. The result is often a network that can be solved using the traditional circuit analysis techniques. We have three different types of diode equivalent circuits. The first one is piecewise linear equivalent circuit, second one is simplified equivalent circuit, and the third one is ideal equivalent circuit. In a piecewise equivalent circuit, the diode can be represented with its barrier potential and its resistance and the diode. So we will be having 0.7 volts and resistance and the diode. So the graph will be in this way. And in the simplified equivalent circuit, we will be having the voltage, barrier potential and the diode. So the graph will be in this way. It will be at 90 degrees, and in this the graph will be at the current will be at some angle. In this it will be at 90 degrees. And for the ideal device, we will be having only ideal diode. We will not have any voltages or resistors. So the graph will be in this way.